Hi, in this video we're gonna talking about how do we calculate the internal energy change or enthalpy change for ideal gas. Before we start with this, we have to have a very clear concept that for ideal gas, the internal energy, enthalpy, Cp, specific heat at constant pressure, Cv at constant volume, they are all function of a temperature. Okay. So in another situation, we could say if we want to try to find delta H and delta U for ideal gas, basically the only thing changes because it's a temperature, right? Temperature, it depending on the temperature. So the first method number one, it's going to be the most probably easy way to do, is look at ideal gas table in your book. And that's going to introduce us some new tables. That's table A17 and up. So let's take a look at it. Let's look at what's table A17. A17 is ideal gas property for air, okay? A17. So in this table, you can find out, for example, you have only temperature here at this column, and H and U depends on the temperature. Then you can find the corresponding internal energy and corresponding enthalpy. A17 is air. Now let's look at A18. A18 is also ideal gas, but now it's what? Nitrogen. So they also have those H and U depends on the temperature. The only thing I want you to watch out between 17 and 18, other than the air versus nitrogen, is this: they have a H bar and U bar. We know enthalpy is kilojoule per kilogram, and H bar, which is kilojoule per kilomole, the same thing for internal energy, kilojoule per kilomole. It's not hard for us to change that to per kilogram, right? We just needed to have molar mass involved. And because molar mass is kilogram per kilomole, so we just need a using this H bar divided by molar mass, then we should be able to get enthalpy as kilojoule per kilogram. All right, so that's the difference. Now let's look at table A19. What substance do we have? We have oxygen, right? So it's also in H bar and U bar, which is kilojoule per kilomole. Then A20 is carbon dioxide. So you see it's all different substance so far. And A21 is carbon monoxide. And A22 is hydrogen. A23 is ideal gas for water vapor. A24 is monatomic oxygen, and A25 is hydroxyl. All right, I think that's where it ends. So that's ideal gas table. Then that will be really quick for us to figure out how to solve it. And then method 2, we're going to use delta U. Remember, we started with delta U is equal to CV dt, right? And here we're going to take out the CV, even though we know CV is a function of a temperature, but here we're going to assume it's going to be a constant. So what constant will we be using? We're going to use CV at this average temperature. Then we're going to use times delta T. And this T average is going to be basically initial temperature plus final divided by 2. The same thing if we want to find the delta H, we're going to use here instead of CV, we're going to use CP at this average temperature, then times delta T. So that's our method number 2. Method 3, which we don't normally use, but I will write it down anyway. That's going to be delta U equal to this CV dt, but this delta H equal to CP dt. And where do we get the CP coming from? That's coming from our table A to C. And here I will show you what table A to C is. A2C is basically telling us CP bar, again it's per kilomole, and then they have this polynomial equation A, B, C, D, those are constant. They plug it in and then you do this very tedious integral, then we can find it. Okay, so now this is a basic. I think the best way to learn this is going to be going through an example, and then let's see. Alright, so here's the example. It said air, so that's going to be considered as ideal gas. And initial temperature, T1, is 300 Kelvin. And initial pressure is 200 kilopascal. Then it's heated at constant pressure to final temperature, T2 at 600 kilopascal. So P1 is equal to P2. Okay, then they want to find out the internal change in internal energy change. So basically find out our delta U. Delta U. Okay, so here we're trying to find the internal energy change, so delta U. So now think about this problem. It's ideal gas, and it's asking us to find internal energy change. So that's fit, and I guess really for engineering problem, very important thing is problem recognition. So this is a problem for internal energy change for ideal gas, exactly for this topic. Then we know there are 3 different methods we're talking about we can use. Now let's use in the first method, using table A17. So table A17, it's going to tell us exact value U1, which means it's at 300 Kelvin. What that value is. We also can find the U2 that is at 600 Kelvin. What's the internal energy is. So let's go take a look. At 300 Kelvin, we're going to go back to table A17. And at 300 Kelvin, we have U as 214.07. And that's have a unit of kilojoule per kilogram. So now go back to A17 and look at 600 Kelvin, and we're gonna get U for air, that's 434. For 34.78 kilojoule per kilogram. Okay, so that's our U1 and U2. Then since this problem they didn't tell us the mass, so likely they are talking about the change in internal energy. That's the specific internal energy, which means per kilogram, right? So this situation delta U is going to be U2 minus U1, and 434.78 minus 214.07. Then that's going to give answer for that. 220 kilojoule per kilogram. Okay. Yeah, so method 1 is very straightforward, isn't it? Now let's look at method number 2. Method number 2, we're going to use the the average temperature. So the average temperature, T average, is going to be T1 plus T2 divided by 2. Our T1 is 300 Kelvin, T2 is 600. So the temperature is, at average, is 450 Kelvin. And in order to find our delta U, we're using CV, okay? Finding delta H, we're going to use CP. That's the difference. So here, we're going to use CP, I'm sorry, we're going to use CV at this average temperature. Then we're going to times delta T. That's our formula for method number 2. In order to do that, we're going to look at CV at 450 Kelvin. And our temperature difference is going to be T2 minus T1. All right, so first step, where do we find out 450 Kelvin, our CV? That's from our table A2B. Okay, so let's take a look where that is. So we're going to look at the table A2B. But before we do that, I want to just talk about table A2 in general. Table A2 have 3 different mini tables. The first one is at 300 Kelvin. 300 Kelvin, that's about 27 degrees Celsius. That's about room temperature. And they give us the CP, CV, and the specific heat ratio K, right? And sometimes there's a method you can use 300 Kelvin to approximate. We can do that for this problem too. Also, table A2B is giving you a different temperature, not just at 300 Kelvin, because we do know CP and CV for ideal gas change with the temperature. And when temperature increases, CP, CV increases as well, right? So that's our table A2. And table H, that's table A2B. Table A2C, however, is giving us this equation, polynomial equation, and then have A, B, C, D. Then you can go ahead and integrate for it. Now let's go back to this problem. This problem, our average temperature is 450, I believe, right? So it's 450, and then if we're going to look at table A2B, and it is air, so we look at the air column, and we're lucky there's a 450 here at 450, and we're gonna look at trying to calculate internal energy, so we are looking at CV, so that's gonna be 0.733. So let's go over here. We're gonna look at 0.733, and that has a unit of kilojoule per kilogram per Kelvin, and T2 minus T1. Final is 600 Kelvin, and initial is 300 Kelvin. So then go ahead, we can calculate that and see what we have. 0.733 times 300. That will give us total of 219.9 kilojoule per kilogram. Then you can start to compare this value with what you got from method number 1, table A17. They're very similar, right? Very similar. And which one is more precise? That's right, method number 1, because that's like exact value. Here, method number 2, you are using the average temperature and using the specific heat at average temperature to approximate. All right, so method number 3, we talk about later, it's going to be using table A2C. Bring that value in there to integrate. I'm actually not going to use that one because it's very tedious. Now I'm actually going to be looking at another method. If I'm going to call method number 4, is method number 4 is very similar to method number 2. It's delta U is equal to CV, but here instead of using average temperature, we're going to just use 300 Kelvin since we have that available, right? The table. So that's going to be table A2A. This will be more appropriate when you have a temperature that is close to 300 Kelvin. If it's not, this estimate might be a little off. So if that's the situation, we're going to use table A2A to solve. Now let's go back to this problem. At 300 Kelvin, what's going to be our CV. So that's table HUA. And we're looking at the air. And air CV is 0.718. 0.718 kilojoule per kilogram per Kelvin. Then you can start to look at, you compare this value is 0.733. Be mindful, 0.733 is from when temperature is 450, and that would be a better approximation than 300 Kelvin. However, they are pretty close, right? Then you times T2 minus T1. In that situation, we have 0.718 times 600 minus 300. You see, it's the same method. It's just that CV value or CP value you are getting is slightly different. And the answer for this will give us as 215.4 kilojoule per kilogram. Okay. All right. So if you compare these three answers, they are relative similar, and the method 1 being the most precise, and the method 2 is going to be relative precise, and the method number 4 is just a rough estimate. So here for this problem is trying to determine internal energy. Here I want to extrapolate. If they want you to find delta H, what would that be different? Here, just go ahead and find H, right? It's 300 Kelvin, same ideal gas table. And here, what would be different if you want to find delta H? The difference is instead of CV, we're going to use CP, and we're going to use same average temperature 450 and times delta T. Same thing for method number 2. In order to find delta H, we're going to use CP at 300 Kelvin and then times delta T. So that's all. That's the difference between delta U and delta H. It's a CV and CP difference. All right, that's all. I'll see you next time. Bye.